Alright, so welcome to review for the final exam for BIOE 3310. This is an old exam from summer 2, 2018. So I think the format we're going to follow for this review session is basically, I'll have a problem up here. You can pause the video and try to work it out yourself. And then I'll proceed with going through the solution. So if you haven't tried to work out this problem by yourself on your own, take a moment now, pause the video, and then we'll come back and do it. All right, so hopefully you've had a chance to pause the video. This is basically one of these non-dimensionalization type problems. So, so we want to get our peak pressure as a function of these whole bunch of variables. So right now we have one thing that's a function of 1, 2, 3, 4, 5, 6 one-dimensional quantity that's a function of a bunch of other dimensional quantities. We want to reformulate this in terms of some non-dimensional groups, and we can basically, they actually tell us how they want us to non-dimensionalize the left-hand side. So we'll do our other three non-dimensional groups right here. So let's go ahead and do that. When we do these types of problems, we build a chart where we start out with each of the variables as one of its columns. So we'll do peak pressure right here, and then we'll do volumetric flow rate amplitude, the length, the diameter, the density, the fluid viscosity, and the frequency of oscillations. So we'll give each of these columns. We'll give each of these columns as well. And I'm just going to double bar this just so we have the left-hand side distinct from what's on the right-hand side. So under each of these columns, the first step what we do is we write down what the units are for each of these things right here. So pressure, we might think of this in terms of pascals, but of course pascals are secretly a bunch of other types of units. Pascals are newtons per square meter. We might need to do a little bit more work here, but that's basically where we're going. This volumetric flow rate amplitude is basically going to have meters cubed per second, right? Even though it's multiplied by sine of something, the units. This is a volumetric flow rate. So this amplitude also has to be a volumetric flow rate, meters cubed per second. Length and diameter are of course meters. Density is kilograms per cubic meter, and viscosity is kilograms per meter second. A frequency, in this case, it's it's multiplied by time within the argument of a sine. Frequency has units of 1 over time, or 1 over seconds in this case, right? So hertz, but hertz are really 1 over seconds. So these are all the units for all of these quantities here. And what we're going to do is we're now going to say, hey, wait a second, we have newtons on the left-hand side here. We have some other stuff right here. These newtons are actually secretly other types of units within them. So if we think about a newton is a kilogram meter per second squared, but then we have meters squared in the denominator here. So this left-hand side is actually kilogram per meter second squared. So that's basically what's going on here. All right, then what do we do? Well, we recognize, hey, we need to get rid of some type of unit, and then we need to choose some other term that has that units in it to then divide everything or multiply everything that has that units to try to cancel those units out. So in a previous lecture, I basically said, hey, it's often good to leave meters and seconds to the end, because those basically have multiple powers, and you might end up kind of getting rid of extra powers or of meters and seconds. So things that typically are to powers like seconds squared or meters cubed, it's usually good to leave those to the end. So oftentimes it's a good choice to pick something that isn't to multiple powers, like kilograms first. We see here that we're looking on our left-hand side to have peak pressure divided by viscosity as one of its terms here. Well, viscosity, kilograms right here. So let's now use we're going to use viscosity to cancel all instances of kilograms for things both on the left-hand side and the right-hand side. All right, so now we've gotten rid of viscosity because we're now using this in other groups. Frequency doesn't have units of kilograms, so that's just going to stay how it is. We notice that density has units of kilograms, so if we divide density by viscosity, the kilograms in both of them will cancel out. Neither length nor diameter have units of kilograms within them, so we can leave those alone. Same with volumetric flow rate, amplitude. Pressure has kilograms in the numerator, as does viscosity, so we need to divide peak pressure by viscosity in order to have those cancel out. So now let's write down what all the units are of our new things. We've gotten rid of viscosity. Frequency is still 1/seconds. Kilograms per meter cubed divided by kilograms per second ends up having something with seconds per meter squared as its units. This group has seconds per meter squared. We still have meters cubed per second, and then kilograms per second squared divided by kilograms per meter second. We end up with units of 1/seconds right here. All right, for this term right here, we're actually getting pretty close to our goal here. So our next sensible choice might be to use frequency to cancel seconds in all of our terms, right? And if we notice that if we do that, we're going to end up with our desired term right here. So let's go ahead with that. We're now eliminating frequency, and we already eliminated this. We notice we have seconds in the numerator here, 1/seconds in the denominator right here. So that means we need density times frequency over viscosity to get rid of the seconds in these terms. Length and diameter are still unaffected, but we now have our volumetric flow rate, amplitude, and we notice if this has seconds in the denominator here, then we'd need to divide by frequency. So we'd have like 1/seconds in the numerator and 1/seconds in the denominator to get rid of seconds entirely. And the same rationale applies here. We have 1/seconds here, so we need to divide by f to have those 1/seconds canceled. So now we have peak pressure divided by viscosity times frequency. And now, of course, the next step is to write out what types of units all of these terms have. So if we notice, we've actually formed a non-dimensional group right here. So unitless right here. Here, this has units of meters cubed. Length and diameter are still meters, and this rho times frequency over viscosity is going to have units of 1/meters squared. And of course, we've gotten rid of these two columns. All right, so we need a little more space to work. We'll formulate another row right here. So all right, so now basically the only thing left is units of meters, and it's actually it's totally up to us, what we choose to cancel out meters, right? We could do L, we could do D, we could do rho f over mu, right? We could do whatever we wanted to cancel out meters, right? I guess we could use the square root, 1/√of this term to cancel all the meters. It's up to us. It's an arbitrary choice, so we can do whatever we want, whatever to cancel meters, right? So we could do D or L, whatever. It doesn't matter. Anything would result in the formation of non-dimensional groups. Again, this just tells us sort of how many non-dimensional groups might exist. It doesn't necessarily tell us exactly what the form of this function would be. So, so for the purposes of this problem, it doesn't matter which one we do. But if you were sort of wanted to maybe experimentally or otherwise come up with a function to describe these dependencies, some formulations might be more convenient than others. But that's beyond the scope of what we're talking about for this problem. So I'm just going to choose D to cancel out all instances with meters. So we already have peak pressure over mu times F. That was unaffected. Here, for this term, this QV divided by F, we have meters cubed here, so we need to divide by d cubed in order to cancel all three instances of meters. L, we would just do L over D. We're using D, and we've already used these other two right here. Here we have 1 over meters squared here, so if we multiply by D squared, then that's what we get down here. And if we look at it, this is unitless. This is unitless. Unitless. We got rid of these three terms, and this is unitless as well. So we've successfully now determined that this desired non-dimensionalized non-dimensional group right here is going to be a function of three other non-dimensional groups. 1, 2, 3. Again, if we chose a different length here, we would have three slightly different non-dimensional groups, but we'd still end up with three groups. So the details of how these groups might be formed, could be different, right? If I took this thing right here and multiplied it by L over D, or divided it by L over D, this could still be a non-dimensional group. It would just be a slightly different one, but I would still end up with three non-dimensional groups right here. All right, so that's this process of forming non-dimensional groups, and you can imagine, if we wanted to determine the relationship between these things experimentally, it would be a heck of a lot nicer to test only three different groups of three different knobs that I need to twiddle to affect the output, as opposed to 6 different knobs that I need to twiddle to affect the output. So the benefits are in terms of our convenience for characterizing these things experimentally. All right, to address the second part, describe a biological or bioengineering system where this type of analysis might be helpful. Well, lots, right? So the first thing that comes to mind, here we essentially have a sine wave flow rate, and we might be interested in pressures. So this might be something like a heartbeat, right? Every time our heart beats, we get some volumetric flow rate that fluctuates versus time. I mean, our heartbeats, the fluctuations is a little bit more like this. So strictly speaking, this might be like a sine wave superimposed with some average, some non-zero average velocity. But give or take a little bit, the oscillating effects would be kind of characterized by this. So so examples might include blood flow. If we imagine if I'm breathing in and breathing out through my lungs, I'm going to have some, maybe not strictly speaking, sinusoidally oscillating flow rate in my trachea or brachial tubes, but it's going to be oscillating. So to get a first approximation of what breathing flow rate through my trachea or other airway passages might look like, this might be a good example. And why might I care about how pressure relates to these things? Well, I might be interested in how much stress is the breathing putting on the walls of my trachea or other things like that, right? So breathing might play a role here, either sort of natural or particularly, we're in the middle of a COVID-19 epidemic right here. We might be interested in if we had some forced oscillations. If I wanted to prescribe some forced oscillation flow rates into out of someone's lungs, for example, for ventilation, I might be interested in, hey, I want to make sure that I'm not putting too much pressure, on this person's soft tissues, right? So these might be some examples that we care about for problems like this. All right, let's move on to another problem. So take a moment now, pause the video, try to work out this problem if you haven't already, and then we'll come back. All right, so what is our goal? Our goal is to get the volumetric flow rate between these plates per unit depth, right? So we're looking for a volumetric flow rate divided by, I mean, they say it's a width W into the page. So it's, just imagine that we're sort of extruding this situation and we have two flat plates, like this with this porous material, between them. So our goal is to get this volumetric flow rate. So we're going to use a velocity profile to get a volumetric flow rate. So anytime you're looking for relationships between like velocities and volumetric flow rates, or other things like that, this is saying, hey, this is going to be a conservation of mass type problem that we're going to want to work out here. All right, so our goal is to basically use this velocity profile and the idea of conservation of mass to show that this volumetric flow rate is equal to this equation or this equation. So let's work it out. So here's just a side view of what this flow might look like. This y velocity, if you'll notice, if I evaluate this at y equals minus h, then I have like minus h right here, which is h, which is the same term as this on the bottom. And if I put y equals minus h right here, then that's the same as this on the bottom. So then this whole term, if I evaluate it at minus h, this whole term ends up being 1. So I have 1 minus 1. So I essentially have 0 velocity at y equals minus h. If you noticed, I've defined y to be in the center line of this plate, right? So I get 0 velocity right here. And then also if I plug in h, it's like minus h, this whole thing cancels out. I have 1 minus 1, so that cancels out. So I basically have 0 velocity at the bottom and the top. And then if I plug in, for example, 0 right here, I'm going to get some maximized flow rate. So basically, what does it look like? This flow profile kind of looks, it's not exactly parabolic, but it's kind of bulgy. So we kind of get our max flow in the middle and we get 0 flow right at the edges. So we have this velocity profile and we're essentially going to say, hey, we're going to figure out how much volumetric flow rate arises from this velocity profile flowing out. And we're going to try to match that to some volumetric flow rate going in. But of course, we sort of need to picture this a little bit more in 3D. So imagine it looks a little bit like this, where I have these parallel plates that are the boundary right here. I'm given this information about this velocity profile right here. So we're basically saying, hey, I have this velocity profile that's kind of bulging. That's kind of bulging out like this. I might want to define a control volume that allows me to relate a volumetric flow rate in, which I'll kind of treat as like an unknown. I'll relate our volumetric flow rate in to this velocity profile out, right? So we have some as of yet unknown volumetric flow rate that essentially flows into this face right here. Then I have this outlet face right here. That's and this is my Vx as a function of y. And we're assuming that this isn't really varying with z. So what can I do? Well, I can apply conservation of mass to essentially this pink box. This pink box that I've flown here or drawn here. And we'll have two different faces, one face that's associated with the volumetric flow rate in, and another face that's associated with this given velocity profile out. So conservation of mass basically says d dt, of an integral over the volume of rho dv is equal to minus an integral over the surface of rho times v dot n dA. So this is what we can do here. I think they, in the problem statement, well, they don't we don't explicitly, it doesn't explicitly say in this problem statement, but this Vx as a function of y is not a function of time. And because this is not a function of time, we can basically assume we're steady. So if this flow out is steady, then the flow rate in is probably also steady. Our whole system is probably also steady. So if our system is steady, we know that this whole left-hand side is basically going to be 0. This right-hand side we want to break up the integral over that whole surface into a couple of integrals. I'm just going to call this left surface surface 1, this right surface surface 2, and we'll call the rest of them, we'll call everything else surface 3. So everything else is going to be surface 3. So what might that look like? Well, we would have 0 equals the integral over surface 1 of rho v dot n dA plus I guess plus negative the integral over surface 2 rho v dot n dA plus negative the integral over surface 3 of rho v dot n dA. We assumed in the problem statement, they say it's sandwiched between two large impermeable plates. If the plates are impermeable, then there's basically nothing flowing out of the top or the bottom, and the problem doesn't sort of explicitly state this, but we can basically assume there's no flow out of top, bottom, or the sides. And by sides, I mean like these two sides here and here. So if we assume that there's no flow out of the top or bottom or sides, basically there's no velocity at any of these surfaces. So this term basically goes away. If we assume the flow is incompressible and homogeneous, if the fluid is incompressible and homogeneous, then density can essentially come out of each of these integrals. And if it comes out of each of these integrals, I can essentially divide through by the whole thing. Sorry, I forgot a minus sign right here. So density essentially comes out of each of these integrals here, and then we can just divide it out for the whole term. Then we're left with, what are we left with? We're left with 0 equals minus the integral over surface 1. So the integral of v dot n for surface 1, well, v is going this way, and n is pointing this way. Right? That's essentially whatever velocity we have on surface 1 and whatever normal vector we have on surface 1. So these are going to be in opposite direction, so it's minus. And then that integral of that v dot n, an integral of v dot n dA, is essentially a volumetric flow rate. So what does this mean? We essentially have a volumetric flow rate. So sorry, 0 equals, we have minus, and then this integral is essentially going to be of minus volumetric flow rate for surface 1. So we have one minus sign here because this is minus, and then we got this other minus sign because v is in this direction and n is in this direction, and then we replace this whole integral of v dot n dA with a volumetric flow rate, sort of by definition. Then for surface 2, so we have minus the integral over surface 2. We already pulled out and divided out rho, so v dot n, well, n is pointing this way for surface 2, and v is this essentially just this vx that's a function of y. So what's that? We can basically plug in Vx as a function of y right here. Then we know this velocity varies with y, so we're assuming it essentially doesn't vary with, I guess z is this dimension here, but it does vary with y. So that means we're basically going to need to express our dA in terms of dy, where we essentially take this. Well, if we want to express this in terms of dy, what does that mean? We're essentially taking this surface for dA, and we're essentially slicing it up into a whole bunch of thin rectangles, each that have a height, dy, and a width. We know the width of this whole thing is essentially given in the problem statement as w. So that means the dA for each of these little slices is w dy. So if we add out the flow rates through all of these individual slices, if we essentially add up all of those little slices, that's essentially this integral right here. So dA is basically going to be w dy. Then we also need to think about sensible limits of integration. So we essentially want to add up all the slices from the slice at this very bottom to the slice at this very top. If we go back to this diagram right here, they defined y equals 0 to be in the middle right here. So the point at this very bottom is essentially at y equals negative h. And this point at the very top right here is at y equals positive h. So those need to be the limits of integration in y to essentially account for the flow through that whole outlet right there. So we're going to go from y equals minus h to positive h. So our Vx of y is essentially entirely in terms of known and given constants. So once we plug that in, this whole integral will be in terms of knowns and given constants, especially when we evaluate it at the limits of integration to kind of get rid of all the y's. And then essentially we have our volumetric flow rate right here. So we can essentially like bring this to the other side and flip them around or whatever. So our volumetric flow rate is as follows. We have our volumetric flow rate. We can pull w out of the integral right here. So we have w times the integral from minus h to h of Vy. We can put in our Vy. We can put in this Vy expression right here, and basically all of these constants, there are a lot of constants in this equation. It's going to be a little cumbersome, but a lot of these constants are things that we can essentially treat as knowns or givens, right? So what can we do? We have that as here, right? So we have minus dp dx alpha times one minus, and then in our denominator, even though it looks a little messy, e to the minus h square root of 1 over mu alpha plus e to the h square root of 1 over mu alpha. Our denominator, even though it looks kind of messy, is entirely in terms of known constants. And then our numerator is e to the minus y square root of 1 over mu alpha plus e to the positive y. Sorry, I'm just going to divide this out. Just get rid of that, separate that out from the line above it. 1 over mu alpha. All right, so so this is the closed parenthesis of this right here, and then we still have our dy. Remember, we brought out our w out here. dy. Okay, so what does this all look like? Well, we have a lot of kind of messy constants right here. Let's define, since it would be a little tedious to keep writing like square root of 1 over mu alpha, square root of 1 over mu alpha. So let's define a few new constants just to make our bookkeeping a little easier. So let's define let's define a few constants to make the bookkeeping easier. So let's say beta is equal to 1 over the square root of 1 over mu alpha. So instead of needing to write this all the place, I'll just put a bunch of betas in. Let's call e to the minus h square root of 1 over mu alpha plus e to the positive h square root of 1 over mu alpha. Let's call this term, let's define this to be, I'll call it gamma. And let's call minus dp dx times alpha. These are constants. Let's define this to be, I'll call this phi. All right, so beta, gamma, and phi, instead of these somewhat messy terms, might be able to make this this a little bit more legible. So our volumetric flow rate, I can divide both sides by W. So our volumetric flow rate per unit width is now gonna look like this. So we have minus h to h. We now have phi, which replaced this first term, and then 1 minus 1 over gamma times e to the minus y beta plus e to the positive y beta. dy. This is an integral, but actually, I mean, it's not too bad as integrals grow, right? We know how to integrate constants. We know how to integrate e to the something, and we know how to integrate e to the something as well. So this integration is possible. Both in this exam, that was an in-person exam, and in your exam, if it's going to be, regardless of whether it's a take-home exam or in-person exam, I give access to Wolfram Alpha, right? So you could just plop this into Wolfram Alpha if you didn't want to do the integral. If you did want to do the integral, well, let's do those steps right here. All right, so this is a constant that can essentially come out. So this equals when we integrate 1 with respect to y, we get y. And then we have our 1 over gamma right here. And then we have e to the minus y beta. So when we integrate this, we get minus 1 over we get a minus 1 over beta. We get a minus 1 over beta out front. So we get a minus 1 over beta e to the y, so e to the minus y beta. And then here we have plus, we get a 1 over beta e to the y beta. And then this is evaluated from y equals minus h to h. So then if you carry this forward a little bit farther, we get phi times h minus 1 over gamma, 1 over minus 1 over beta e to the minus h beta plus 1 over beta e to the h beta minus h minus 1 over gamma minus 1 over beta e to the plus, it would be plus h beta, right, if I sub in minus beta right here, and then plus 1 over beta e to the minus h beta. This is a little bit messy. I mean, you could certainly keep it the way it is, but I'll just sort of rewrite things to make them a little bit more clear. If you do out all the algebra, you end up with, and sort of, if you can kind of like group like terms and distribute your minus signs and do all that, you end up with 2 times phi times h plus minus 1 over beta e to the h beta minus e to the minus h beta over e to the h beta plus e to the minus h beta. And it turns out that this term right here, this grouping has a special name. It's called hyperbolic tangent, which is tanh of h beta. So this has a special name called hyperbolic tangent, but whatever. If you don't want to put this in terms of tanh, you don't have to. And then of course we could plug in our definitions of beta and gamma, and oh, did I miss gamma? Oh, I think gamma canceled out. Oh no, gamma I sort of expressed. I re-expressed gamma in terms of this denominator right here. Sorry about that. Yeah, so I did that. So I have this result right here. If I want to express it back in terms of mu's and alphas and all that stuff, I could do so here. So I end up with minus dp dx times alpha times 2 of h minus square root of mu alpha e to the h square root of 1 over mu alpha minus e to the minus h square root of 1 over mu alpha e to the h square root of 1 over mu alpha plus e to the minus h square root of 1 over mu alpha. That's my answer, and I'm sticking to it. Sorry, it was a bit of a tedious road to get here. I mean, so the key conceptual thing was setting up conservation of mass. Then it was a sort of another conceptual thing was, how do I define dA? The key thing is, dA you can oftentimes express in terms of like dy or dz or dr or something like that. You typically want your d, whatever you're choosing as your sort of infinitesimal dimension, you want that to reflect what your velocity profile is going to be a function of. Right, so dy, because v was a function of y, we essentially sliced up our wall into a bunch of things here. And then it was just a bunch of tedious calculus and algebra, but we did it. We got to some final result. Success. All right, let's move on to another problem. All right, so this is actually 3 short problems. So take a moment now, pause the video, try to answer each of these 3 problems, or at least answer the first one, and then pause the video when it comes time to come back to the second problem. So we're going to talk about this first problem right here. All right, so hopefully you've had a chance to pause the first video. Houses are constructed with 2x4s leading to 3.5 inch thick insulation, or 2x6s, 5.5 inch thick insulation. So regardless of whether my house is made of 2x4s or 2x6s, I still have the same overall size of my walls. So I'm almost investigating, walls that look like this. So whether these walls are made of 2x4s or 2x6s, the overall size of my wall is the same. It's just the thickness that's different, right? So I'm looking at the wall of my house. Basically, whether it's 2x4s or 2x6s, basically is saying, how thick, what is the distance of these boards you know, how thick are these boards right here, essentially dictating how thick is my wall right here. So this thickness could be either 3.5 inches or 5.5 inches. And then, you know, in addition to the insulation in my walls, there's also, like, you know, sheetrock on the inside and siding on the outside. Strictly speaking, you know, these walls have windows in them, which, you know, provides a sort of different path for the heat to flow through. But I'm saying neglect all those thermal resistances of all the other stuff. Let's just consider this how wall thicknesses affects it. So if we assume steady conduction in a 1D slab, we can use thermal resistances for this problem. So they're saying, you know, by what factor would the thicker walls reduce your energy use? So if I'm thinking about energy use, you know, if you know, energy use is essentially like how many joules of fuel my furnace burns per month. You know, joules of fuel per month is essentially asking how many watts, or or something that is equivalent to watts flowing through this. So essentially, we're looking to investigate what is the Q conduction through this wall in either of these cases. And thermal resistances allow us to relate a temperature difference to a heat flux. So regardless of whether my house is made of 2x4s or 2x6s, I'm still going to want my inside temperature at some temperature. And, you know, the outside temperature is essentially dictated by the weather, right? So we're basically saying, hey, my delta T is something that I'm just going to take as a given. My cross-sectional area, normal to which, you know, the area that's normal to the direction of heat flow, is something that's taken as a constant. So I can basically say, hey, I'm just going to say that there's some L 3.5 and an L 5.5 that correspond to these two, and I essentially want to say, hey, what is the convective heat flow, the watts that flows through this wall? And so here, and I mean, yes, I'm investigating one wall here, but you could imagine just scaling this up to all of the walls in the house and kind of getting the same answer. So I might, so, you know, by what factor would thicker walls reduce your energy use for heating? You know, essentially I'm asking, you know, what is the Q dot conduction for the 5.5 inch walls in ratio to conduction for the 3.5 inch walls? Well, in general, Q dot is equal to delta T divided by thermal resistance. So the ratio of these Q's is essentially going to be, you know, 2 delta T's divided by 2 R's. So delta T, well, actually I said this is I'm treating as a known constant, and this is going to be the R for whatever is the 3.5, or sorry, the 5.5 in the numerator, and then delta T divided by whatever resistance I have for the 3.5 in the denominator here. So I can reformulate this, the delta T's cancel out, so I end up with the ratio of whatever the resistance of the 3.5 is divided by whatever the resistance of the 5.5 inch thick walls is. For the 1D slab, the thermal resistance is proportional to the thickness. Thicker walls are better thermal resistors, divided by the thermal conductivity of whatever makes up the insulation material, which, regardless of whether you use 3.5, whether you use 2x4s or 2x6s, you're still putting that pink fiberglass insulation or whatever insulation you have in those spaces. So, you know, that's just how it is. So that's going to be the same for both of them, divided by the cross-sectional area, which we said, you know, I still have the same size house regardless of whether I'm making it with thick walls or thin walls. You know, the size of my room is still going to be the same. So what does this mean? We basically have L 3.5 divided by K K times AC divided by L 5.5 divided by K AC. The K's and AC's cancel out, so then we basically just end up with 3.5 divided by 5.5, which is equal to 0.64. So the factor of reduction, so basically I cut down 36% off my heating bill. So what's the moral of the story? Well, we can combat global warming by increasing, by for example, when we construct new houses, making them have thicker walls, or if we want to retrofit old houses, sometimes what you can do is you can sort of add a layer of insulation either to the insides, or if you're residing the exterior of your house, you can, instead of just putting the siding where you found it, put down another layer of insulation and then put new siding on the outside. So if we make the walls of our houses a lot thicker, we can cut down on global emissions by burning less fuel to heat our homes. All right, so next up we have this problem right here, and it's essentially asking us about the relationship between pressure drop and flow rates through pipes. So here we have it right here. It's essentially saying, hey, there's some delta P that's essentially driving a volumetric flow rate. It's essentially driving a volumetric flow rate through the pipe, and then it's saying, hey, what if we doubled the tube length, but we kept flow rate and diameter, and presumably the same type of fluid the same. All right, so we have steady laminar flow. If we have steady laminar flow of a Newtonian fluid with a constant circular cross-section, they don't give us any information if like the tube is vertical or horizontal, so I think we'd need to assume that the tube is horizontal. If we have a horizontal steady laminar flow of Newtonian fluid, then we can use fluidic resistors, right? Fluidic resistors are essentially the best shortcut to relating pressure drops and volumetric flow rates. So if you use fluidic resistors, the pressure drop is equal to the fluidic resistance times the volumetric flow rate. So we can use fluidic resistances. If you dust off your notes from the lecture on fluidic resistances, there's a formula that gives fluidic resistance, and it's basically a function of viscosity and the tube radius or the tube diameter, as well as the length. So what can we do? Well, we can basically say, we can form a ratio between delta P for the short tube and delta P for the long tube, and then formulate that in terms of a ratio of fluidic resistances, and then see how that plays out. So let's say we're looking for a ratio between delta P for the short and delta P for the long. And we can essentially say that this is the same as the fluidic resistance for the short tube times the volumetric flow rate divided by the fluidic resistance for the long times its volumetric flow rate. We said that the volumetric flow rate and the tube diameter, so the flow rate's going to be the same, so those cancel out. And we can plug in the equation for fluidic resistors, either in terms of diameters or whatever. So if you do it in terms of radii, the equation is 8 mu L times 1 over pi r to the fourth. And we said we're keeping radius constant, so that's just r, and the same fluid, the same Newtonian fluid, so L, but the length, this one would be the length of the short tube. And then we could have the same equation here in the bottom, 8 mu L long times 1 over pi r to the fourth. The 8 mu's cancel out, the 1 over pi r to the fourths cancel out, so at this point it's just the ratio of the lengths of the tube. And we said, hey, we're going to double the tube length, so that basically means the long tube is twice as long as the short tube. So if our short had a length of, let's say, one arbitrary unit, the long tube would be twice as long. So this means, if the ratio of the pressures is essentially the same as the ratio of the lengths. So if we doubled the tube length, this here basically means that we would double the delta P, right? So if we went from a short tube to a long tube, then we'd have to go from a small pressure to twice that pressure. So we double the P. All right, so let's take a look at this next one. So you can pause before we proceed. All right, so hopefully you had a chance to pause. Here we are. So there's this, we continue to have a steady laminar flow, Newtonian fluid, constant circular cross-section. So this basically says, hey, we could use fluidic resistors if we wanted to, again. But this question kind of gets at a different point here. How would the shear stress on the wall change if we were to double the flow rate but keep the pipe geometry and stuff the same? So it turns out there are basically two ways to approach this problem. So let's consider the first case. So the first one is actually not going to be fluidic resistors. If we know we have steady laminar flow in a circular pipe, this basically says, hey, we're going to have that parabolic. We're going to have that parabolic velocity profile, right? We're going to have this parabolic velocity profile where basically the z velocity as a function of r is going to have some v max in the middle, and it's going to be parabolic, so it's going to be like 1 over r squared over big R squared, where big R is the radius of the whole pipe. If you look back in the notes, I forget which one, I don't know if it's notes or homework, somewhere back in the class, for this parabolic velocity profile in a pipe, the max velocity ends up being twice what the average velocity is in a pipe. You could prove this with conservation of mass if you wanted to as well. And we also know that the average velocity is basically just the volumetric flow rate divided by the cross-sectional area, or in this case the volumetric flow rate divided by pi over, would be divided by pi r squared. All right, so what can we do? We can basically plug this in here. So our parabolic velocity profile is basically going to be 2 times volumetric flow rate over pi r squared times 1 minus r squared over r squared. All right, how is this going to be useful? Well, velocity profile, schmalosity profile, mostly what we're interested in is shear stress on the wall. So what can we do? We can say, hey, wait a second, shear stress is going to be the following. Well, we know shear stress is related to velocity gradient. So we'd say tau rz is equal to minus mu times d vz dr. And if we wanted this at the wall, we would say minus mu, and it would be d vz dr evaluated at little r equals big R. So what can we do? We can take our velocity profile that we have here, that's in terms of volumetric flow rate, we can plug that into this equation here and then see how does wall shear stress, what is the relationship between wall shear stress and volumetric flow rate. So we can do that. Tau wall is equal to minus mu. We can plug in our velocity profile here, so it would be the derivative with respect to r of 2 times volumetric flow rate over pi r squared, 1 minus little r squared over big R squared, evaluated at little r equals big R. Well, we can take this derivative, this first term, it's just a derivative of a constant, so it's 0. The second derivative, we can bring this down, so we end up with minus mu times 2 volumetric flow rate over pi r squared. We get a minus 2, the minus from here and the 2 from bringing down this, and then we end up with little r over big R squared, and this whole thing is evaluated at little r equals big R. Well, we plug that in, and you end up with your wall shear stress is equal to 4 mu volumetric flow rate over pi r cubed. So what does it mean? If we had volumetric flow rate and doubled it, then the wall shear stress would also double. So double volumetric flow rate would imply double the magnitude of our wall shear stress. Sorry, it's a little sloppily drawn tau, but there we have doubling this. That's the first way that we could go about doing this. An alternative way to do this is to think about it in terms of fluidic resistors. So what do fluidic resistors say? Well, fluidic resistors basically say, hey, the pressure drop is equal to the fluidic resistance times the volumetric flow rate. And so if we doubled the volumetric flow rate, we would double the pressure. I could also basically consider this cylindrical chunk of fluid in here, and if I did conservation of momentum, and in particular z momentum, right, because z is in this direction, if I did conservation of z momentum, I would have my accumulation equals ins minus outs plus generation for momentum, no accumulation because I'm in steady state. My ins and outs would be the same. I have the same velocity profile as out, so my ins and outs cancel each other out. And so my generation is basically just 0 equals the force due to pressure plus the force due to shear stress. And I don't have any gravity or through solids, so it's basically just these two. So it's basically saying, hey, force due to pressure and force due to shear stress need to balance with one another. So my force due to pressure is just delta, I have this pressure, this upstream pressure pushing this way, this downstream pressure pushing this way. So the net pressure force is just going to be delta P times pi r squared, the area of this face right here. So it's going to be delta P times pi r squared. Right? And I guess since delta P is formulated as P in minus P out, this prescribed this way, is indeed in the positive z direction. Then my shear stress force is defined in this way where, positive shear stress sort of points in this direction. If I kind of imagine this chunk of fluid right here, we said positive shear stress points to the right, negative shear stress points to the left. So my shear stress force is basically just the force due to this shear stress is going to be minus tau wall times the area that shear stress is acting on. And the area that shear stress is acting on is this outer rectangle, if I essentially unwrapped it. So what does that look like? It's basically tau wall times whatever length, times the length of tube that I have, times 2 pi r. So this is essentially the area of this unwrapped rectangle, which is the area that shear stress is acting on. All right, so what does this mean? I can basically take delta P and I can plug this in terms of volumetric flow rate. So what does that look like? 0 equals my fluidic resistance times my volumetric flow rate times pi r squared minus tau wall times L times 2 pi r. And I can, of course, plug my fluidic resistance, my equation for fluidic resistance in terms of radius and stuff right there, which is, this fluidic resistance is 8 mu L times 1 over pi r to the fourth. And then if we see, we get a whole bunch of stuff here, But once we plug all that stuff in, basically like the L's factor out and a bunch of R's and stuff factor out, we can see here that if we solved this for tau wall and we doubled QV, then we would also double tau wall. So if we plug this in an algebra, we would end up with the same equation for tau wall that we had right here. So we can basically go about it two totally different ways, and reach the same conclusion that doubling the flow rate would double the shear stress. All right, let's look at our next problem now. All right, so take a moment, pause the video, if you haven't already worked it out yourself. All right, so we want to determine the velocity profile. And by velocity profile, we're saying velocity as a function, velocity in some direction as a function of some coordinate. We have a non-Newtonian fluid, so we can't necessarily just rely on like Navier-Stokes or something like that. And it's in the gap between this spinning inner cylinder and the stationary outer cylinder right here. So we could sketch the shape of the shell that we'd use to determine this velocity profile. So when we're thinking about shells and velocity profiles, the key to shells and velocity profiles is choosing our delta dimension. And when we think about velocity profiles, we want to think about velocity in some direction that's a function of for shells anyway, only one variable, right? So what direction do we anticipate velocity being in? Well, I'm going to try to draw this 3D a little bit here. So here I have my inner cylinder. Here I have the outer cylinder. If my inner cylinder is spinning at this velocity here, but my outer cylinder is not spinning, I'm basically going to have this situation where the fluid very close to the inner cylinder is moving fast, and that velocity kind of tapers off as I get close to the edge. So if I'm thinking about this, I have concentric cylinders and stuff like this. This idea really screams, I should probably work in some kind of cylindrical coordinate system. So if I'm thinking about working in a cylindrical coordinate system, I might define R as this direction right here. I might say Z is this direction right here, and theta would be like an angle from some points kind of around the Z axis right here. So if I'm thinking about this, in what direction are we going to have velocities? Well, the fluid particles are essentially just going to be traveling around in little circles, kind of following points on the cylinder that are essentially moving around in little circles. So what does it mean? We're basically going to have a v in the theta direction. And with this rationale here that the fluid particles close to the inner cylinder are moving at some velocity and the fluid particles close to the edge aren't moving at all, we would anticipate velocity being a function of r, right? So we're going to have velocity in the theta direction, but that is a function of r. And when we choose our delta dimension, you almost always want to choose your delta dimension to be in the direction of or along the coordinate that you anticipate velocity varying, right? So velocity varies with r, so we're going to choose r as our delta dimension. So I'm just gonna try to draw this again a little bit bigger. So if this is our system here, we're going to want to choose r as our delta dimension. Choosing r as our delta dimension basically says, hey, we're going to want our shell to sort of be sliced like this with some thickness delta r. We don't really anticipate that this velocity is going to vary in any other direction, right? As long as there's not some weird stuff happening very close to the surface or very close to the bottom, we wouldn't anticipate much variation with z. And just as long as, you know, these cylinders are truly concentric and we, you know, don't have anything weird going on, you know, there's not really anything making this zone different from this zone versus from this zone, so there's not really any variation with theta, right? So we really only need r as our delta dimension, and that basically means that our shell can sort of be a hollow cylinder that is concentric and coaxial with all of the rest of the stuff here. So the shell can just go like this, where its thickness is delta r, it has a distance r from the center to the inner part, and r plus delta r to the outer part. Its circumference would be, of course, related to these, and it doesn't really matter if you make its height delta z or the full L. You would end up being able to derive the velocity profile in the same way, right? So this dimension could be delta z or L, doesn't matter, because we don't really anticipate any variation in velocity with z anyway. So that's how we form shells. All right, let's move on to one more problem, the big one. So take a moment now, pause the video if you haven't worked out this problem already, and try to do it on your own. All right, so here we have it. We're looking, so we have this system here. First, we want to show surface heat flux of the pipe needed to accomplish the temperature change, this watts per meter squared, talking about thermal entrance length, asking for average convection coefficient, and then asking for temperature at the outlets of the pipe, right? So here, you know, we have this average convection coefficient. This part of the problem is just screaming, you know, hey, this is like a find your own H type problem, and if we're going to find our own H, you know, as a function of like fluid properties and characteristics of the flow, we're probably going to need to do Nusselt numbers, definitely in part C. Asking about thermal entrance length, we're going to need to bring up those equations there. And then surface heat flux, you know, here we're probably going to need to do some sort of conservation of energy type thing, right? So here we're going to need conservation of energy. Here we're going to need the equation for thermal entrance length. This is probably going to be via Nusselt number, and since we're dealing with flow through circular pipes, it's probably going to be in terms of an average Nusselt number, sub d. And then surface temperature for the pipe at the outlet, you know, this surface temperature, you know, surface temperature is related to average temperature and all that stuff. Average temperatures information is given up here at the outlet anyway, right? So if we're thinking about surface temperatures, a relationship between surface temperature and average temperature is going to be via Newton's law of cooling, perhaps using that H that we just found here, right? So these are going to be the problem-solving strategies we use for this section. So let's get started with this first one. All right, so what's the key piece of information in this first part? It's saying needing to accomplish this temperature change. And this temperature change, we're talking about an inlet temperature and an outlet temperature. We have information about a flow rate. So let's kind of sketch out and tabulate some information that's going to help us for the first part of this problem. Well, we essentially have our pipe right here. We have our T in and our T out, and of course these are mean mixed temperatures for the inlets and the inlet and outlet right here. And then we have this pipe, and this pipe is basically dumping heat. You know, it's dumping heat into all of the walls of this thing here. So we essentially say, hey, you know, there's some temperature of the flow going in and some temperature of the flow going out. We kind of consider this as energy, thermal energy carried by mass in, thermal energy carried by mass out. So the difference in those thermal energies carried by the mass must be essentially accounted for by the power from all of the heat flux that's entering the walls. So if we think about things this way, we can define a control volume that's essentially just barely on the inside of the pipe, and we can formulate conservation of energy right here. So we have our constant surface heat flux, which I'll call Q sub S. And our goal is to basically show that this is going to be 131 watts per square meter. So we have this system as follows right here. We essentially have we can apply conservation of energy. They're talking about flowing the solution through here, and I don't think there's nothing really in this problem statement that implies anything unsteady about this problem. So we're going to have our accumulation equals our ins minus our outs plus any generation. If we think about accumulation, this is going to be 0 because we're steady. If I think about my ins, I essentially have some energy carried by mass. Some energy carried by mass going in. I also have an inlet that's the sort of overall Q from this QS, and I'm just going to call this Q convection. That is essentially the accumulation of all of this heat flux. All of this heat flux essentially is this heat flow due to convection, and then that's it for my two ins. Then I'm going to have my out, which I'll call E dot out for energy carried by mass out, and so long as my control volume I defined to sort of be on the inside of the pipe, that way it doesn't include the heaters, there's no generation, right? So basically my CV is inside and heaters are outside, so they're not in my control volume. So I don't this generation term. If I had put in the heaters for this generation term, then I would essentially be double counting this thing right here. So what does this boil down to? We basically say 0 equals my energy carried by mass in minus my energy carried by mass out, plus the convective heat flux that's essentially entering the side. Well, I can relate a heat flow to a heat flux. If that heat flux is uniform, all I can do is just multiply that heat flux by whatever the area of the sort of unwrapped rectangle that makes up the surface of this pipe here. So that's basically, so what does that look like? My heat flow is essentially equal to my as of yet unknown heat flux times times the area that heat flux is passing through. The heat flux, the area that piece of is passing through, we know the pipe diameter and we know the pipe length, so I can basically just say times pi dl. So this essentially gives me a relationship between heat flux, area, and heat flow, which I can then plug in right here. If I think of energies carried by mass, well, energy carried by mass in is going to be proportional to a couple of things, right? Well, we can think, the first thing is going to be proportional to is this volumetric flow rate, right? So it's proportional to this volumetric flow rate. Remember, all of these terms need units of watts, right? So this is watts per meter squared, meters in meters. So this term has units of watts. This term has got to have units of watts as well. My volumetric flow rate is going to be meters cubed per second. And then if I take that volumetric flow rate and multiply it by the fluid density, we'll sort out density in just a second, but I'll be able to read it off this chart, so we can sort of treat it as a known constant for now. That's going to be kilograms per cubic meter, right? So basically, the more mass that's flowing in through this inlet surface, the more energy, the more thermal energy is carried by mass in. And then I could also multiply this by the specific heat of the fluid, which is essentially for every kilogram of fluid and every degree C you raise it, how much energy does it store? So that's basically going to be joules per kilogram Kelvin. And we see we're getting awfully close here. And then, of course, the thermal energy carried by the mass in is proportional to its temperature as well. So we can basically say that's the flow, essentially the flow rate of energy carried by mass at the inlet. And I could do a similar thing with the outlet. The only difference would just be T out right here. So I can plug that in as well. So this is a little sidebar over here. So what is this going to look like? It's basically going to be 0 equals volumetric flow rate times density times Cp times T in minus T out plus this convective heat flux term. And what is that going to look like? Well, that's just what we had over here. So we have our QS pi dl. And remember, this convective heat flux is defined by going from the solid to the liquid. So that's kind of why I treated it as an in. So what does this mean? This basically gives us all of the information we need to solve for our as of yet unknown surface heat flux. And that's basically equal to T out minus T in. Again, if I bring this stuff over to the other side, I'd be flipping the order by essentially factoring out a minus sign. Volumetric flow rate, rho Cp, divided by pi dl. So these are knowns. These are right, T out and T in. Those are given in this part of the problem. D and L, those are given. Now, density and Cp, we haven't fully sorted this out yet. And strictly speaking, these are not constants. And actually, strictly speaking, these should have been slightly different for the inlet and outlet that I have here. And we need to kind of get these from the chart. Right? But these things vary with temperature. So what temperature do we use? Well, we have 62 degrees C and 72 degrees C. So, on average, or somewhere in the middle of the pipe, on average, these two temperatures, I'm sort of taking averages of averages, right? So these are essentially averaged across the cross-section, but I sort of want to average it also over the length to kind of get one single temperature that describes, for the most part, what the temperature of this fluid is. So I can basically say, hey, I'm just going to average these two, so I'm going to use 67 degrees C. And of course, 67 degrees C, we got to translate to Kelvin. You translate it to Kelvin, and it ends up being 343 Kelvin. There's that 273.15 difference between degrees C and Kelvin. So we add that to 67, and here we are. So what does this mean? We basically can now look at 340 Kelvin, and this gives us all of the properties. This gives us all of the properties that we need for density and specific heat, viscosity, and thermal conductivity is, of course, something these two we'll use later, but these two we got to use now. So we plug those in for our terms here. You put it all in, and you end up, and you can just take my word for it that if you plug in all of the right temperatures and all this stuff, of course you need to be careful to translate millimeters to meters and work out all the units. But it does indeed end up being 131 watts per meter squared. So we've made our conclusions about part A. Part B, can thermal entrance length be neglected? Well, for thermal entrance length, we of course have to use the equation for thermal entrance length. there was an equation for that. There's an equation for thermal entrance length in the notes. And it basically says, hey, there's thermal entrance length, and there's but there are sort of two different versions of it, one for laminar flow and one for turbulent flow. And of course we need to know, there are two different equations for thermal entrance length, one depending on whether your flow is laminar or turbulent. So what do we need to do? We need to calculate whether this flow is laminar or turbulent. And the one for laminar depends on Reynolds, the equation itself depends on Reynolds number anyway. So, so no matter what, it's gonna be unavoidable. We're gonna need Reynolds number factoring in here. So our Reynolds number based on diameter is density times average velocity times diameter divided by viscosity. And the average velocity is equal to the volumetric flow rate divided by the cross-sectional area, which is equal to the volumetric flow rate divided by pi over 4 d squared. So you plug in, the volumetric flow rate, that was a given, pipe diameter, that was a given, right? So we can plug this in, and when you plug it in, you end up with, I forget what it is. It's like 0.006367 meters per second or something like that. You can check me on the numbers, but that's anyway what I had here, right? So this gives us all the information we need for velocity. We of course, we have density, which we just got from the chart right here, and pipe diameter, which was given to us, and viscosity now is something that we can read off the chart as well. You plug it all in, and you end up with a Reynolds number of 29.7, which of course is less than that critical number, which I think it's like 2,000 or 2,200 for pipe flow. So this flow is definitely laminar. So if it's laminar, that means we need to use the correlation for thermal entrance length. So use the laminar correlation, where our thermal entrance length is going to be equal to, it was 0.0567 times Reynolds number times Prandtl number times diameter. Of course, the equation I think was given, sorry, I'm using capital D and lowercase d interchangeably here, but whatever. So we have D, we have Reynolds number. Prandtl number, if you remember, is mu times Cp over thermal conductivity. So now we got to rope in our thermal conductivity as well. You plug in those properties for Prandtl number, and you end up with 2.665 if you plug in the values and do all your units properly. So you plug in this Prandtl number here, you plug in this Reynolds number here, you plug in 2 millimeters for your diameter, and you end up with a thermal entrance length of 0.00898 meters. And if you think about this is a heck of a lot less than 1 meter right here. So we can definitely neglect our thermal entrance length, because this is much, much less than L equals 1 meter, the total length of the pipe. Great. So, sweet. So, can thermal entrance length be neglected? Yes, via this analysis that we've done here. Again, remember, there's no hard and fast cutoff for what this threshold should be. It's not like it's not like Reynolds number where there's like a very clear distinction between laminar and turbulent flow. This is just something where it's like, does it seem small? If it's how small is small? It's a judgment call, but it's up to you to kind of explain your rationale. For this one, yeah, definitely. All right, now part C. Show that the average convection coefficient is this 1439 watts per meter squared Kelvin. If we want to think about, so this is basically saying this quantity right here is an H, And strictly speaking, it would be B and H bar essentially averaged over the whole length of the tube. But since entrance length makes such a small difference, whatever. So what do we got to do? We got to find our own H. So if you remember, we need to find H, and we need to find this via the Nusselt number. Now remember, we did 2 lectures on these Nusselt numbers, one for flat plates and one for pipes, so we want to make sure to look at the ones for pipes. And to be extra clear, the Nusselt number sub d is based on the diameter of the pipes. What is the relationship between H and Nusselt number? Nusselt number sub d, sorry, I should be writing this in black because this is something that's as of yet unknown. Nusselt number sub d is equal to, and this H, I guess I could put this H in red because that's something that we care. Well, whatever, we'll just put it in black. So Nusselt number, you can remember, you can kind of think of it as a normalized H. It's basically H times D over K of the fluid. Right, so D and K are known, so as soon as we find Nusselt number, that gives us all the information we need to find H, which was the goal for this problem. But if you remember this Nusselt number is essentially a function of Reynolds number, Prandtl number, etc. And we had these various cases where we sort of needed to ask ourselves, a couple of questions. So the questions that we need to ask to use the correct Nusselt number equation from our chart is it constant surface temperature or constant surface heat flux? In this case, it's constant surface heat flux. I mean, that's the whole part of the whole first part of this problem that we were trying to solve. The second thing that you need to ask yourself when thinking about Nusselt numbers is, can we neglect the thermal entrance length? In our case, yes. Yes, we can. And then the final question that we need to ask ourselves is the flow laminar or turbulent. We concluded that the flow was laminar already from this part of the problem right here. So with answers to these questions, we look at the chart from the lecture notes, and we conclude that Nusselt number sub d is equal to 4.36. So actually, it turns out this, in this particular special case, it actually wasn't really explicitly a function of Reynolds number and Prandtl number for this regime of flow. Although conclusions about Reynolds number helped us to get here. So what does that mean? We take this Nusselt number and we can now plug 4.36 back into this equation. That gives us everything we need to find H. So our H is now equal to 4.36 times K over D, which when you plug it in, 4.36 times 0.66 watts per meter Kelvin over 0.002 meters, you end up with our desired 1439 watts per meter squared Kelvin, which is what we were shooting for. Success. Finally, what is the surface temperature of the pipe at the outlet? Well, Newton's law of cooling essentially allows us to relate, for flow inside of pipes, it's a relationship between surface temperature and the mean mixed temperature in the pipe. Well, we already know the mean mixed temperature at the outlet, and we're looking to determine the surface temperature. So we'll essentially treat this as an unknown. This is a known, and of course Newton's law of cooling will involve this H that we just found. So how's that going to play? Well, Newton's law of cooling says that the surface, we can do Newton's law of cooling on the per unit area. Oh, sorry, I'm off screen. Sorry, we can do Newton's law of cooling on the per unit area basis, which says heat flux is equal to convection coefficient times our as of yet unknown TS, I'm treating surface heat flux as a known because we figured it out in part A, and H I'm treating as a known because we figured it out in part C, and that's TS minus Tm, and this would be Tm at the outlet if we want TS at the outlet. So we can use the sort of outlet surface temperature, which is what this problem is asking for. And the mean mix temperature, you solve for it and you end up with TS is equal to QS over H bar plus Tm at the outlet, and the TS at the outlet is this. So we plug in our QS, from part 1, we plug in our H from part C, and we plug in our given Tm at the outlet, and you end up with 72.09 degrees C, which is like super duper close to this 72 degrees at the outlet. Right? So, and actually, you know, from an engineering perspective, that's really good. That's really good for doing PCR. Why is that really good for doing PCR? Well, if you're doing PCR, you don't want the stuff at the surface of the tube to be, you know, at a different temperature from the stuff at the center, because then, you know, your annealing and your extension and your denaturation, like that's all going to be off, right? So, you know, it's good that this surface temperature doesn't differ too much from the mean temperature, right? The mean temperature was 72 and this was 72.09, so we were super duper close. So I guess that's a benefit of using microfluidics for this problem. All right, so hopefully this was helpful in your preparation for the final exam. Thank you very much for listening, and good luck with your study of heat transfer.